The ocean rises like a wall, satellites tumble, and the stars slide across the sky without warning. Earth is not being swallowed yet. Somewhere nearby, an object with no surface and no light has entered our neighborhood. The first clue is not darkness, but motion. The moon's path begins to change, while satellites quietly lose their predicted positions. Then observatories realize something massive is passing close. This is the first twist. A black hole is not automatically a cosmic vacuum cleaner. Far away, its gravity behaves like any object's gravity with the same mass. So the outcome depends on three things: its mass, its trajectory, and how close it comes. The label alone tells us almost nothing. To understand the nightmare, rewind to the moment before anyone notices. Imagine an unseen mass crossing the outer edge of Earth's environment. At first, nothing strikes the ground, and no alarm sounds. The black hole may remain invisible while the geometry of nearby orbits quietly changes. Astronomers would first see stars shifting against their predictions. Their instruments would detect a gravitational disturbance before human eyes saw any object. Satellites would need constant corrections, and navigation systems could drift from their expected paths. The danger would arrive as a growing pattern, not one explosion. The moon could be perturbed, and Earth's tides could behave strangely. Water would respond first because gravity is already moving every ocean twice daily. If the visitor passed far enough away, Earth might survive intact but leave its old orbit. The planet could be redirected without being touched. That means the immediate consequence is not necessarily a crater. It is a planet whose relationship with everything around it has suddenly changed. Now shrink the black hole dramatically to roughly 10^-115 grams. That is about 1 billion kilograms, comparable to the mass of a large mountain compressed into a tiny object. If such a primordial black hole crossed Earth, it would not necessarily swallow the planet. Its passage could leave a narrow gravitational disturbance, shock waves, and seismic vibrations. A modeled transit for that mass-deposited energy comparable to a magnitude 4 earthquake. Cities could feel a sudden, mysterious tremor without seeing the cause. The disturbance would be narrow compared with Earth's width, not a planet-sized strain. The object could pass through and continue onward, leaving vibrations behind. Each whole number increase in earthquake magnitude means roughly 32 times more released energy. A localized passage therefore becomes terrifying only when the disturbance scales upward. The same name can describe a mountain mass object and a stellar mass object. Their effects are separated by an almost unimaginable difference in gravity. Now imagine a black hole with roughly one sun's mass. Its event horizon radius would be about 3 kilometers, roughly the scale of a small city. That radius sounds small beside Earth, but the mass is not small at all. A close pass would pull the near side more strongly than the far side. That difference is called a gravity gradient, or tidal force. It is the gradient that turns an ordinary gravitational pull into planetary destruction. The oceans would surge toward the visitor, while the atmosphere and crust began responding to the unequal pull. Coastlines would stop behaving like coastlines. Earth's equatorial diameter is 12,756 kilometers, giving the tidal force a planet-wide distance to work across. The near and far hemispheres would be pulled apart differently. At first, people might interpret the changes as separate disasters. Then the tides, satellites, moon, and ground would reveal one enormous cause. A 10 solar mass black hole would have an event horizon radius of about 30 kilometers. That is metropolitan scale, carrying stellar mass inside a dark boundary. If that object passed close enough, Earth's orbit could be destabilized before the event horizon ever touched the surface. A near miss could become an orbital exile. The sun might still shine, yet Earth could no longer follow its familiar route. Gravity would rewrite the neighborhood before the darkness arrived. But direct impact is the most visually dramatic possibility. Once the event horizon intersects Earth, matter cannot escape by any route through space. The horizon is not a solid surface or a wall. It is a boundary where escape would require traveling faster than light. Rock, water, and atmosphere would fall inward, collide, and heat up. The black hole itself would still be dark, but its feeding material could glow. A visible or X-ray bright disk would form only if gas, dust, or disrupted planetary material spiraled inward and heated. Darkness alone is not evidence. Near the horizon, tidal forces can stretch matter dramatically, a process commonly called spaghettification. Earth would be torn by gravity before becoming a simple falling stone. The crust would deform, oceans would stream outward, and the planet's shape would lose its familiar meaning. The disaster would unfold across Earth before disappearing beyond sight. Imagine watching the horizon bend while familiar continents stretch into glowing ribbons. Every human map would become a memory before the planet was gone. Yet there is another unsettling possibility. The black hole replaces the sun without gaining the sun's light. Earth's orbit would remain essentially unchanged, but daylight would vanish. The solar wind would disappear as well, even though gravity would continue holding Earth's orbit. Same mass means same pull, not the same warmth. The planet would become a world of artificial lights and lengthening cold. Humanity might survive the gravity perfectly while losing the star that made survival possible. A black hole with Earth's entire mass would have an event horizon roughly 9 millimeters wide, about the width of a pea. Compression changes size, not gravity's source. But calling it Earth's black hole does not determine what happens next. A tiny event horizon can still represent a mass spread through an entire planet. For scientists, the first challenge would be detection. For everyone else, it would be realizing that ordinary-looking skies no longer obey yesterday's predictions. The evidence might begin with stars, tides, and satellites rather than a glowing monster. Invisible objects are often revealed by what they move around them. People would film the sky, call relatives, and search for explanations while emergency teams watched the shorelines. Fear would arrive before certainty did. There would be no universal evacuation plan for a black hole. A microscopic transit, a near miss, and a direct stellar encounter demand entirely different responses. A narrow passage might leave shaking ground, but a living planet. A close stellar mass pass could instead deform oceans, destabilize orbit, or tear Earth apart. The science is surprisingly simple at the beginning. Outside the event horizon, gravity follows the same mass-dependent rules that govern every orbit. Double the relevant mass, and the gravitational influence changes accordingly, move closer, and the gradient between near and far sides becomes stronger. Distance sharpens the danger. That gradient is why a black hole can be harmlessly distant yet devastating nearby. The event horizon is not the first danger, unequal gravity is. For a small primordial object, the gradient can be concentrated into a narrow track. For a stellar object, it can span the planet and amplify everywhere. The event horizon explains the final one-way boundary, but not the glowing disk. Light comes from matter heating as it falls, not from the hole itself. That distinction matters for the human eye. We might not see the intruder until the ocean, atmosphere, or broken planet began making it shine. And humans are not abstract observers here. Every shifted tide means a harbor. Every tremor means a bedroom. And every darkened sky means a family looking upward. The most frightening moment might be the quietest one. A normal street, a normal night, and stars moving where nobody expects them. Then the ground answers, the tides climb, or the sun goes dark. The universe reveals itself through consequences before explanations catch up. So what if a black hole came to Earth? The honest answer is not instant swallowing, but a branching map of mass, distance, and path. It might shake a city, erase sunlight while preserving an orbit, rearrange the moon, or destroy the planet through tidal forces. One label hides 4 different nightmares. The black hole would not need to be hungry, angry, or aimed at us. It would only need the right mass and the wrong trajectory. That is the reframe. Black holes are not defined by what they swallow first. They are defined by how gravity reshapes everything around them. Would humanity recognize the invisible visitor before the first tide rose? Or would the sky keep it secret until Earth began to move?